My apologies, students. I was going to upload this earlier, but my setup kind of got messed up. So I'll try to do it as we can. We're going to go over 1.2 and 1.3 today. This is all review from Algebra 2 and Geometry and Algebra 1. So if you're confused at all, feel free to ask questions. Primarily, if you have confusion, it will be about probably the word problems and how they word it. But since we're not doing the book's examples per se, it shouldn't, the homework from the book, we shouldn't technically have that big of an issue, but you can always ask me. So I'm going to go through the notes. Now, keep in mind that there's these vocab. You do not need to know them. You don't need to memorize them. It's all in the book, and I'll talk about a few of them. First, equation in two variables simply means we're going to be dealing with y and x primarily. There might be a few things where we'll add, like especially word problems where you'll have different variables like c and b and p and t and all these, but primarily x and y. A solution to an equation implies that you can put a ordered pair or a point. So you plug that point in, and it's going to, both sides of the equation are still going to equal. An example here is example 1. You have this point. We're checking if these 2 points, which one lies on this line. You start with 2 and 13, so you plug 13 in for y and 2 in for x. So this becomes 20 minus 7 is 13. Does 13 equal 13? Yeah. Okay, so that is a solution. So you can in fact say the point lies on the line, okay? And then the other one does not. So whenever it doesn't equal, you say it's not a solution, okay? Now our method for sketching graph, there's actually 2 methods. I've learned students prefer the first one, but actually the second one's more useful. So first, does the point hold true? So if you plug it in the point, the equation should still be equal, okay? If it's not equal, that means the point's. So here's our process. If possible, you isolate one variable. So an example where you might want to isolate a variable, so if you have x, y equals 6, you're going to get y equals 6 over x. Okay, that's just isolating the y, so the x should already be on the other side. Generally, it's y, but there's a few cases where you might want to isolate x, and there's a few cases where we won't. Okay, and then you make a table, and generally you're going to make a table with a few points, or several points, maybe like 6. But the time it takes to make tables is kind of tedious, so there's an easy way, and then you plot those points, and you always connect it with those points with a smooth curve or a line. So smooth curve, everything that's not linear is a smooth curve. Everything that is linear is a line. So my favorite word, the smooth curve, has come back. Okay? So sketching these 2 graphs, this one's pretty easy. Now linear, you don't have to do it this way. This seems kind of ridiculous for linear. But like this one, you definitely can use a table for this point. Sorry, we'll zoom in a little bit. There we go. So for x squared minus 2, you can definitely use a smooth. You can use a table and then plot the points. Now, is there a second way we can do this? Absolutely. So first, before we start the second way, finding intercepts. So how do we find the x-intercept? X-int is to plug 0 in for y. Okay? And then, it's amazing, y-int, plug 0 in for x. They might say substitute. Let's look at the book real quick. So, we're going to skip over to intercepts. To find the x-intercept, let y be 0 and solve the equation for x. Okay, that is the mathematical way of saying it. This is Mr. David way. Notice plug isn't a mathematical word, so obviously they don't like to use that. Okay, using symmetry. Now, the interesting thing with symmetry is, right, the idea, symmetry is if I have an image, this, and I have a line of symmetry, then the other side of the image should be equal. Like, you should be able to flip it. Now, you see mine's not exactly equal, but it works better with plotting points. So if you have point, 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 a line of symmetry through it, then there should be a point here and a point here. And then if you draw the line, okay, so you should get this symmetry, okay? So basically symmetry allows you to graph with fewer points. That's what symmetry is all about, graphing with fewer points. So there's a few more aspects to graph, okay? So a graph, now this is a graphical test for symmetry. So if you're in the book, we go to symmetry and notice there's three types of symmetry: x-axis, y-axis, and origin. Origin flips. It's a cool image. Okay, graphical test for symmetry. A graph is symmetrical with respect to, my apologies, 1 second, to the x-axis if whenever we have the point x comma y on the graph, then the point x comma negative y is also on the graph. That implies that x-axis means that the y, the x will be the same for the opposite y's. So think of it like this. If I have the point, 2, 3 on the graph, then this implies, if we're symmetrical with the x-axis, that 2, negative 3 is also on the graph. So if you were plotting it, it'd mean that 1, 2, 1, 2, 3, 1, 2, 3. It'd mean that if this point is on the graph, this point's also on the graph, okay? Okay, that's the symmetry, okay? So let's then do y-axis. Okay, the graph is symmetrical with respect to the y-axis if whenever, notice we always start with the basic point, xy. If xy is on the graph, then negative x comma y is also on the graph. What's that mean? That means if we have the point 2, 3, with y-axis, it implies negative 2, 3 is also on the graph. So with y-axis, that would mean that if we have this point, we also have this point, okay? I'll use different colors next time, this time. So this is the x-axis, and this is y-axis. Okay? Now, we have one last one. If a graph is symmetrical with respect to the origin, whenever x comma y is on the graph, then the other point, which is the opposites of both, is also on the graph. Okay? So origin is an entire flip. So origin, not origin the person, origin the plate, the location. So if we flip it, what's also going to be on the graph is negative 2, negative 3. So origin is going to be here. Okay? So y-axis goes this way, x-axis goes this way, and origin goes this way. Okay? Now, if you look at the book, it does show you these things. Okay? So we're gonna look at the algebraic test, and we're gonna go over by a few minutes because of just filling in. Okay, so these all will be pretty close. Okay, so I'll go quickly. So graph of an equation is symmetrical with respect to the x-axis if replacing y with negative y yields an equivalent equation. Okay? The graph of the equation is symmetrical with respect to the y-axis if replacing x with negative x yields an equivalent equation. And then graph of the equation is symmetric with respect to the origin if replacing x with negative x and y with negative y yields an equivalent equation. Okay? So basically, with respect to x-axis means you're changing the y to negative y. And then you plug that in, and if it works, then that's symmetric with the x-axis. Y-axis is x with negative x, and it should give you the same answer. And then origin is replacing both x and y with negative x and negative y. Okay? So we're going to look at example 5 on the next video. We'll actually just move through these quite quickly, okay? Yeah, so we have quite a few pages left, but we can get